My name is Marty Paris. I'm in the Dallas office for Kimley-Horn. I'm one of the Trenchless Technology practice leaders with the firm. And first of all, I'd like to say thank you to NASTT for their support for our industry in providing educational opportunities like this free webinar. I personally benefited from participating in the National No Dig Conference, as well as our regional South Central chapter events. And I highly recommend the good practices courses that they provide on all the various trenchless technologies. And so there is still time to register for the upcoming good practices course on HDD or horizontal directional drilling that's coming up here in September. So I encourage you to sign up for that as well. That course is 8 hours long, so it'll go in much more detail than what we'll be able to cover here in today's webinar, but we're excited about the opportunity to share with you. Let me go to the next slide. So your presenters today, there are 5 of us from Kimley-Horn. All of us are practice leaders who work on primarily water and wastewater projects. Each of us will share a case study of a project that utilized horizontal directional drilling on the project. There are some more detailed bios in the handouts if you're interested in learning more about each of us, but we'll be available at the end to answer questions, and we'll probably reach out to people who also have questions that aren't able to be answered during the webinar today. So we look forward to meeting and getting to know each of you as have the opportunity. Well, as we get started, I thought it'd be appropriate to just give a very brief definition of a horizontal directional drilling. This definition is actually the official definition that is shown on the NASTT website. So, horizontal directional drilling is a surface-launched trenchless technology for the installation of pipes, conduits, and cables. HDD creates a pilot bore along the design pathway and reams the pilot bore in one or more passes to a diameter suitable for the product, which is pulled into the prepared bore in the final step of the process. So that's kind of a simple definition. It can be used for lots of different utility or pipelines. We're going to be talking mostly about water and wastewater pipelines, pressure pipelines that are going to be used for installing it. Here's a simple illustration that kind of show what it looks like. Typically, HDD is used to be able to go underneath an obstruction that would be very difficult to install the pipe by open cut. So bodies of water is a very typical installation for HDD, going under roadways or railroads, trees, airport runways, things like that. So typically, the horizontal directional drilling rig would be set up there, like on the left side of the illustration, with an entry pit, and then the drill pipe and the drill bit would be drilled into the ground, and you would have a design path that you would lay out before the project, knowing where you're going to be heading. But that drill bit can be steered from the surface. There's some ability to steer that, and it's typically tracked as well along the path to make sure that you're following the drill path length. But once it goes out to the other side at the exit pit, at that point is where you would install the reamer on the end of that drill pipe, and then it would be pulled back, and you would make the hole larger. And if it takes more than one pass, then you would do that multiple times until it's to a point where you can pull in the product pipe or the pipe that you're using for the crossing, and that would be laid out there on the exit pit side on the right. So that's a simple kind of description of horizontal directional drilling. Again, today's purpose is to introduce some of the topics that will be covered in the upcoming HDD good practices course. We're going to share some key takeaways and lessons learned from 5 different projects that utilized horizontal directional drilling. And then at the end, as we mentioned, there will be a time for some interactive question and answer. So the presentation will probably be around an hour, 60 minutes or so, and then we'll have plenty of time for discussing questions and talking about different topics that people are interested in talking about. So with that, I'm going to let Kyle Sanderson start with the first lesson learned.
All right, well, good afternoon, I assume for most of y'all that are out there. So the first case study that we're going to talk about today is a project that we did for the city of Frisco. It's called the Legacy South 20-inch Force Main. So for those of y'all that are not familiar with the Dallas-Fort Worth Metroplex, so Frisco is a city about 25 miles north of Dallas. It's a city that's been rapidly expanding really over the last 2 decades, one of the fastest growing cities in North Texas, with a population of close to 230,000 now. And it's also home to some pretty famous names. So the Dallas Cowboys, PGA of America headquarters, and soon to be Universal Studios all call the city of Frisco home. So zooming in a little bit more on our project specifically. So our project was at the north end of Frisco, just west of the Dallas North Tollway. So in the map there, our project is shown in the bold black line. It's generally along Panther Creek Parkway and Legacy Drive. Ended up being about 10,300 feet of 20-inch force main. Of that, 7,000, little over 7,000 feet was open cut, 1,400 feet was auger bore, and then 1,700 feet is horizontal directional drill. And those limits of directional drill is what's shown there in pink on the map, and that's what we're going to spend the most of this case study talking about. So first question that we're going to talk about is why did we decide to go with horizontal directional drill? So as we started on the design phase of this project, there were several different project constraints that we took into account as we decided how we wanted to approach the project. So the first one had to do with a state DOT crossing, TxDOT. So in the aerial there, you see El Dorado Parkway at the top of the screen. So that is a DOT road. And TxDOT has very specific requirements about how they'll let you cross the right of way. Specifically, they don't allow any open cut construction across their pavement. And they also have some very specific requirements on what they'll allow from a trenchless perspective as well. So that was one of the things we had to work through as we started designing this project. The next one is the existing buried utilities. So Legacy Drive, you can see is fairly built out there. The parkways on both the east and west side of the road, those have a lot of heavily congested with franchise utilities. And then the city had an existing 10-inch wastewater line and a 24-inch reuse line located in the median. So unless we wanted to entertain an option where we open cut underneath pavement, there wasn't a great location to put in this new force main. And then speaking of pavement, so you can tell from the aerial there, there's 2 different colors of pavement. So there's a dark gray, which represents the older pavement in the area, and then there's that lighter gray color. So that's all the new pavement that the city had just recently put in place. And so as we started the design, the city was pretty adamant of, hey, we don't want to rip up pavement that we've just recently put in. And then the last piece there is the horizontal curve. So you can see Legacy Drive has a pretty good curve there. So that limited the different trenchless technologies that we're able to utilize without having multiple entry and exit pits. So as we moved into design, we ended up with 3 different installation methods that we evaluated schematically. So we came up with a schematic design for open cut, auger bore, and horizontal directional drill. And we came up with opinions of probable construction costs for each one of those. So ultimately what we ended up finding is that open cut was the cheapest option, but it was also the most disruptive because we were going to putting the pipeline down 1 lane of traffic. So we'd rip up the entire pavement for that lane, and obviously the traffic impacts that come along with that. Auger bore, because of that horizontal curve, we ended up having a lot of entry pit and exit pits. Ultimately, this was pretty disruptive because of the pits and also pretty expensive. And then lastly, the directional drill. So we were able to incorporate both the horizontal and vertical elements into that design. So we were able to limit it to a single entry and exit pit. So it wasn't very disruptive, and ultimately the cost ended up being about the same as open cut. So at the end of the day, we ended up going with the horizontal directional drill. From a pipe material standpoint, so really there's typically 3 different pipe materials that we'll look at. There's fused HDPE, there's a restrained joint PVC, similar to like a Certalock, and then there's your fused PVC. So the city doesn't currently have any HDPE in their system, and they didn't want to worry about having to maintain another pipe material in their system, so we ruled that one out pretty early. And then similarly, they had some restrictions in their design code where they didn't allow the restrained joint Certalock type product at the time. So ultimately, we ended up with a fused PVC as the pipe material. So now we're going to move into some different construction phase items. So first thing I'm going to talk about is shop drawings. I know it's always really exciting to talk about shop drawings, but I think it's probably pretty important, and I think it's important to talk through how we ended up moving from the design that we had in the contract documents into what actually got built. So as we started the design, we went through the typical design process We referenced our design manuals. We ran the calculations on bending stresses. Talked with contractors about installation requirements, staging requirements, all that. Ultimately, we ended up with our proposed design plan and profile that we put in the contract documents. But ultimately, we had some requirements in our specifications that required the contractor to ultimately be responsible for providing design calculations and then a drill design plan and profile that would be used to construct the force main. We did this for two different reasons. So the first reason was we wanted to open it up for the contractors to be able to utilize the different pieces of equipment that they may have on hand already. We felt this would it would open up their options. It would reduce the cost of the project and increase competition. And then secondly, we wanted to make sure that we took advantage of the contractor's expertise. They do this day in and day out. We wanted to make sure that we took into account of that so that we could ultimately have the most constructable product at the end of the day. So a good example of this was in our design at the north end of the project where we had the exit pit. We had a reverse horizontal curve as well as a vertical curve as we came out at the end of that drill, which from a design standpoint, all the radiuses worked. It worked with the pipe, it worked with the equipment we were using. But ultimately, when we got it in front of the contractor, they had some reservations about how easy it would be to actually construct that. And the analogy they had was it was similar to an airplane when it was coming into land. So if you're on an airplane, you don't want to be coming in horizontally, turning, and also trying to descend. You essentially said you want to keep it as straight as you can horizontally and just focus on your vertical coming in. And so we took that advice and ultimately we changed the design to account for that. Through this process, there were a couple different lessons learned. The first one is how to balance the design intent with the contractor's horizontal directional drill design. So as we went through the shop drawing process on this, we ultimately had a lot of back and forth with the contractor. I think we had 4 different shop drawings that we reviewed and rejected. And ultimately, the challenge was getting what we felt was important during our design wasn't as important to the contractor. So an example was when we designed our profile initially, we had a maximum depth of about 35 feet. When the contractor submitted their first profile, they ended up with a depth of 60 feet, which we felt was way deeper than we were comfortable with. The contractor didn't quite understand some of the maintenance challenges that the city had concerns with long term. So again, ultimately what we decided is if we would have had a workshop at the beginning of construction, getting together with both the design team and the contractor to walk through what we wanted to do, it would have been easier to marry some of those ideas together and hopefully shorten the shop drawing process. The other component there is understanding the project stakeholders. So on this project specifically, we had the GC, and underneath the GC, they had a horizontal directional drill subcontractor. Well, once we got into construction, that subcontractor had some equipment malfunction, and they weren't actually going to be able to drill the job within the project schedule. So they ended up getting another sub underneath them to help with the drilling. And then the GC also hired an engineer to help with the design calculations. So ultimately, they had 4 different stakeholders on the contractor side that were providing input into the shop drawing phase and into this final design. But unfortunately, they weren't all getting brought in at the right time. And so, that kind of helped, or that added to some of the back and forth with the shop drawings. Again, if we would have had a workshop at the beginning, understood better how the whole contracting team was pulled together, we would have made sure that we could have had all the right parties in the discussions from the beginning. The next couple slides here, we'll walk through some construction photos, focusing primarily on the project layout and the staging area. So to help orient you here, we are on the north side of the project, looking to the south. At the top of the screen there, that's where our entry pit was. So we drilled from south to north. And then at the bottom of the screen here, you can see we've got the pipe strung out, and they pulled the pipe back in from north to south. So a couple more photos here of the construction staging. So as we worked through the design process, we decided early on in the project that we wanted to try and keep all of the construction, all the staging, pipe stringing within the medians or the turn lanes. So the city had pretty wide medians in this area, and we felt that would be feasible based on our discussions with contractors during the design process. So as you can see, we've got the pipe strung out here in the top picture, within the median, within the turn lane. The bottom picture here, we've got the fusion machine also within the turn lane. So ultimately, we were able to do what we were hoping to accomplish. So this project, it ended up advertising back in September of 2019, and by the time they got ready to build it, it was April of 2020. We all know what happened around that time period. So obviously COVID had become a thing, and there was not nearly as much traffic on the road. So ultimately at that point, the contractor requested to be able to shut down a lane of traffic in each direction for additional contractor safety and to minimize some of the risks. So they were a little concerned with having their workers within a couple feet of active traffic. And then they also had some concerns that, you know, as they're pulling this pipe into the ground, if you had too much bending stress, there was some sort of pipe failure that could cause a risk to some of the passing traffic. So they requested to shut down the lanes of traffic, which ultimately we allowed given the reduced traffic load due to COVID. And that ultimately worked out pretty well. There wasn't any sort of traffic issues for the city. And then the last slide here is just a picture of the entry and exit pits. So on the left, this is the entry pit. During the design phase, we had worked with some contractors to get an idea of how much space we needed to allow. Ultimately, we ended up with a 50-foot wide by 150-foot long staging area is what we had planned on. So you can see they've got the drilling rig here in the bottom right. They've got drilling rods, they've got an excavator, generator, quite a bit of equipment. They did take advantage, obviously, of the lane of traffic that we gave them back. But ultimately, I think they would have had enough space if they needed to put that all inside that 50-foot by 150-foot working area. And then on the right here, so this is the exit pit. From a design perspective, we're looking at a 50-foot by 100-foot staging area. As you can tell, there's quite a bit less equipment that they were needing to keep on site there, and they were able to stay within that working area pretty easily. So with that, I'm going to go ahead and turn it over to Josh, and he's going to talk through a project that he did in Fort Worth.
Gotta push all the buttons, right? There we go. Well, all right, sorry everybody. Let's keep going. So yeah, thanks Kyle. So this project is in City of Fort Worth. It's just a little bit left of the Frisco one that Kyle just showed us. So this was primarily driven by sanitary sewer system capacity constraints, and so I'll kind of get into the details of that going forward. So in 2018, the City of Fort Worth executed a sanitary sewer overflow initiative with TCEQ, which is kind of the EPA arm in Texas, kind of precursor, you know, avoiding consent decree moving forward. And you know, lots of projects were on this initiative, but one was the Clear Fork project, which is intended to eliminate this sanitary sewer overflow that you can see here. And this is University Drive. It's a major arterial through north-south through the city, right in front of Macaroni Grill. So it's the Macaroni Grill overflow. So a little background on the project. There's Fort Worth's general city limits on the right side of the screen. You can see DFW Airport on the upper right, just to kind of orient. And the Clear Fork Drainage Basin basically drains about 100,000 acres, that southwest quadrant of Fort Worth, some customer cities, and then supporting a lot of growth on that end. Ultimately, all falls into the West Fork Basin at the bottom, near downtown Fort Worth, through a pair of 48-inch gravity interceptors and a 24-inch, and then ultimately into 254s, continuing to the northeast. So here's kind of a look at the alignment. And this is that upper reach of that area, as I mentioned. So you can see the Macaroni Grill overflow, or SSO, right there in the middle with the maroon arrow. And the purple and green lines represent the two interceptors that the city was having challenges with from a capacity standpoint in the near term or now, and then anticipating growth upstream, which would just make it worse. So the solution here was to bring in a lift station, which is kind of a little weird to have in the middle of a system and not the bottom of a basin, and then effectively pump around these choke points in a pretty heavily developed area. Since with a pressure pipe, there's a little more flexibility for installation horizontally and vertically. And so the rest of the focus will be on the force main installation itself and then the directional drill. So this is kind of a similar view, but with an aerial northeast to the right. You can see downtown Fort Worth on the far right. The intent of this was just to demonstrate the different installation methods along the alignment. So you have purple, I mean, very little open, or sorry, I think I have those flipped. Red is open cut, purple is hand mining, and yes, in Texas we hand tunnel where at all possible. That's just what ends up happening. I know it's not common in a lot of other parts of the United States, but the big idea is those 3 green reaches are the 3 directional drills that we did on this project. And then kind of focusing on some of the features there. So you can see Union Pacific, which is always a lot of fun, and the Fort Worth and Western Railroad on the right side, both of those crossed by directional drill. Interstate 30, a local tollway authority, Chisholm Trail Parkway. And Trinity Park, which is the city's premier park, so very visible, very, you know, intending to protect trees. Protecting trees was a high priority of the work that was done here. Okay, so final scope of the project was about nearly 3 miles of 36-inch HDPE Force Main, 5,400 feet of that, which was installed by directional drill. So you can kind of see there the reaches, 2,200, 1,100, and 2,100 feet of DIPS DR11, and then a couple other kind of tidbits on various lengths of other installs for that. And then just because pricing is fun and it's interesting to understand kind of the component, you know, what went into it. This was awarded to a general contractor, local utility contractor, and they subbed. We went through a pre-qualification process to pre-qualify a handful of national directional drill contractors, and you can kind of see there a look. Those 5,400 feet I mentioned on that top row, 1650 a linear foot, 1,400 linear foot, 1,900 and 2,200. Kind of to look at the directional drill pricing throughout the project. All right, so some key features here I wanted to point out on this project. For 2 of our 3 drills, we specified conductor casing to be utilized to kind of protect that entry of that pilot bore. So initially, we in our initial shot, especially at this railroad permit, this is see the UP crossing there. We weren't showing this, but after doing some geotechnical analysis, indicated we wanted to protect that pilot bore, especially with some weaker soils or potential for pathway for hydrofracture at that location until the pilot was fully through. And it had the added benefit of kind of throwing a bone to UP of casing the crossing for a portion of it, of that crossing from right-of-way to right-of-way. Basically, the casing pipe was rammed into bedrock, and through quite a few back and forths on the permitting side, the railroad eventually agreed to let us do this method. Since you can kind of see there on that right picture, we started that turn immediately after the casing, and so we had some geometric constraints that wouldn't allow us to go all the way across the right of way. And then if you can see, I hope you can see, there's a video looping on the left side showing an air hammer strapped to the back of that casing pipe. And then on the right side, you can see there's an auger machine. So as that casing pipe advances through being rammed in place, the auger then augers out the soil that's taken in. And kind of just to go completely opposite of Kyle's scenario that he just explained, we took full advantage of the bendiness of HDPE or plastic pipe on this project to get around a lot of obstructions vertically and horizontally. I'll show some pictures of that. But you can see at the bottom right of that, or bottom left of that picture, lots of trees we're trying to miss, and this is in Trinity Park. And so kind of zooming in, so there's that pipe string laid out along University Drive, and you can see there's some fairly large excavators in that foreground picture top, probably more typical on large steel pipe, but because we had to make such tight bends, taking a hard left right out of the borehole and then another hard right immediately afterwards, some larger equipment than probably typical for a HDPE job. Here's another look at pipe stream layout for the Trinity River crossing. Again, navigating those trees through there, kind of on that right side in yellow. There's some shots of that pipe layout. Again, large equipment and cranes on site to lift the pipe to prepare for pullback for that river crossing. Last thing I'm going to focus on is the Trinity River crossing and a hydrofracture that occurred. Of course, we had 3 drills and we specified conductor casing on 2 of them, and those went great. And this is, well, and we were able to mitigate this, but this is the only hydrofracture that occurred on the project. And just to kind of, maybe I'll dial in on that a little bit. We've had fairly high confidence of our geotechnical information, but this area to the right of the river specifically used to be kind of old landfill, and so there's been a lot of weird. And as we were doing the pipe ramming to the north of here, we actually got some 1950s newspaper clippings from the Horror Star Telegram. So lots of interesting things coming out of the ground here, and so of course our boring wasn't representative of exactly of where that line went in. Okay, so zooming in on the right side there, you can kind of see that there's the directional drill rig set up in red, and then as the pilot bore had advanced about 100 or so feet, we started to see some issues, and you can kind of see this pink storm drain system I've sketched in there. As that pilot bore goes under that Y connection, basically we started, yeah, there you go, started seeing some fluid come through cracks in the pavement, and then ultimately started looking in the river, and some drilling mud started showing up there too. So stop everything, figure out what's going on. Some CCTV revealed that Y, that blue label's pointing at that Y, had a crack in it, and that was a nice pathway for drilling mud to make its way into the storm system and ultimately into the river. So thankfully, this was in August, and it doesn't rain in Texas in August, hardly ever. And so it was pretty simple for the GC to come in, remove a stick of that storm drain, put a temporary plug in, let the contractor continue on, or the drilling contractor continue on. And they also opted to back up the bore, install 16-inch washdown casing to, again, protect, similar to how a conductor casing would protect that pilot bore until the pilot bore was able to enter bedrock and continue on. So a couple lessons learned here. I think, and it's easy to say is, expect the unexpected in underground construction. This was definitely a panic mode of what went wrong and how can we help mitigate it. But sometimes there is no predicting underground conditions as good as we try. And then, as I mentioned before, a nice feature of using plastic pipe, HDPE specifically, is sometimes you don't have the option to kind of make those straighten out your turns as you enter or exit bore pits, and it definitely adds to cost. And we certainly had some back and forth with the contractor, but I think ultimately the GC and the HDD sub was able to work that out because we didn't have a lot of flexibility to change our alignment. So, and it off to Kevin.
Thank you, Josh. All right. Can you guys see my screen? So,
Great, Kevin.
perfect. So today we'll be talking about a project here in Miami-Dade, here in South Florida. This is a 42-inch HDPE Force Main that will be drilled along a state road on 953. All right. So this project consists of 2 directional drills, HD1 here shown in blue and HD2 in green. This is approximately 4,800 linear feet of 42-inch HDPE pipe that will get installed. We're estimating this project to bid approximately from $9 to $11 million. The intent of this force main is to provide a redundant line for Miami-Dade Water and Sewer. So currently there's an existing 36-inch force main along this corridor. However, due to its age, Miami-Dade Water and Sewer is being proactive and wants to install a parallel line that can be used in the case of an emergency shutdown of the existing force main. This is due to pump station 348 being a critical pump station for the sewer basin. So why are we going with directional drills? The main reason for this is the project schedule. So we're working on a state road where in 2026, FDOT, the Department of Transportation, will be coming in and doing their own mill and resurface job for the entire corridor. So we had coordinated with them, and ultimately we were told we have to put the pipeline in before their project goes through. So we evaluated the open cut versus drill option, and we estimated about 100 days of savings in construction time. So we expect this project to take about 350 days in comparison to the open cut portion being 450 days. Another reason why we chose HCD is because a traffic analysis was performed for this corridor, and the results have stated that basically the Department of Transportation would not allow 2 lanes to be closed off during the day due to the heavy traffic. So that being the case, the contractor would have had to install this pipeline at nighttime, where they would have been able to close off 2 lanes at a time. Nighttime work comes with its own challenges, particularly a cost increase, but also it's tougher inspections for the county and for the engineering group. So here's the drilling rig setup that we're anticipating. This is about 150 by 30 feet of work area. As you can see, we're using the drill rig, and the drill pit is on the inside lane, but we are taking advantage of the median that we have available for the ancillary equipment, including the drill rods, the control room, generator, the conics, for equipment containers. As part of this project, we anticipate mud recycling equipment, so we accounted for that in the work area as well. As you can see, here's the pump station 348. So this is on the south side of this project, right? Now on the pipe pulling area, we had to take a close look at the maintenance of traffic in this case. So here's the midpoint of the project, and the bottom part of this picture, you'll see the entry pit for the pipeline. So we're basically stringing all of the pipe to the north of this major intersection. And then once a contractor is ready to actually pull the pipe through during a weekend operation, we're basically closing down the intersection. So you can kind of see here the turn lanes and the westbound, eastbound lanes are being closed off. And the contractor will fuse that final portion of the project, around 270 feet of pipe there in that intersection. So once they have everything fused, then they'll go ahead and begin the pipe pull. So a key component here is that we have to work closely with our maintenance of traffic partners here in our Miami office, making sure that the Department of Transportation understands, how the operations, right, and agrees to allow us to give us a permit. So just big picture on the project, it's split up into 2 phases, the south drill and then the north drill, essentially basically flip-flopping where the pipe stringing would occur. And then phase 3 is a connection of those drills, right? So down the middle of the project, we'll connect those pipelines. And then phase 4 is basically the connections to the north and to the south by open cut construction to existing force mains, right? So this project included a lot of stakeholder engagement, right? Particularly the utility, Miami-Dade Water and Sewer. We're doing some pretty serious bypassing of that pump station 348. So that we had a lot of conversations of what's the best approach there, and I will show a slide on that as well. We're working with the Miami-Dade Expressway, where we're crossing an overpass, a highway. The Department of Transportation was a key component here, considering we're in their right of way. And then we had the city of Opa-locka, city of Hialeah, coordination with them to be able to get their dry runs for the right of way permit. And another concern here was we have a middle school that's along the project corridor. So that took into play where we were planning on stringing pipe so that we maintain access to the school at all times. Here's just a general layout. On the left picture you'll see here is the point of connection to the 36-inch force main where we're tying into. In order to do that connection, which is a 36-inch T, we are proposing a double line stop with a bypass pipe so that we can keep the pump station operational at all times. And then on the north side of the project, we're tying into an existing 42-inch and 48-inch force main as well. So we're using, making sure that we have enough area for the drill rigs, but also for the point of connections, right? So with that, I'd like to pass it on to James to discuss the Cypress Waters force main.
Thanks a lot, Kevin. Okay, so we're gonna head back to Texas and talk about Cypress Waters. So this was actually this is a project that I've worked on for almost my entire career at this point, probably 15 years or so in the running. As a project we were fortunate to just be involved in and engaged with the developer in the city of Dallas since the beginning, where this was just the concept. But what it is it's a large mixed-use development in the northwest part of town, and it has basically a 30-year build-out or time horizon for the development. And so we were engaged in the beginning of just planning, sizing the infrastructure and determining how it would be phased and what trigger points were necessary as the development grew, figure out what needed to be built and when. And then we've just been slowly, installing and constructing that infrastructure over the last 15 years. And so this was a project where I got to design my first lift station way early on in my career, and then actually got to design the replacement of that lift station many years later. And so that's what we're going to talk about today, is actually that replacement lift station. It's a 9 MGD lift station. And specifically, we're going to focus on the force main and the HDD component of that, which was about a third of the force main length was by horizontal directional drill. And we'll get into, again, the whys and the wheres as we go along. But a good portion of it was installed by HDD. And total project cost was around $5.5 million. It was several years ago now. I think it was 2018 dollars. So no doubt would cost quite a bit more in today's time, but that's what it came out to back in 2018. So zoom in a little bit. The Cypress Waters development is the kind of pretty colored graphic there on the left, surrounding the lake. And then this portion of city of Dallas is kind of unique. It's just a little outcropping of the city and like a sliver that's actually surrounded on all sides by other cities. So you've got city of Irving there in red on the right and off the screen to the bottom. And you've got city of Coppell on the left and the top, kind of shown in that blue shade. And so this drill got to go through all three cities and certain portions of it. So you have the force main itself is shown in this yellow line here. The lift station started down here in the development and then traversed over to the eastern boundary of the property, and then went into city of Irving, and then eventually up into city of Coppell, and then traveled through this East Beltline Road corridor. And this is where we had the majority of the horizontal directional drills. We had 4 back-to-back sections of drills, and then we also had a 5th one down here in city of Irving, where we were basically just trying to avoid some environmentally sensitive areas and wetlands that we didn't want to disturb by open cut. So for the rest of the presentation, we're going to focus on this area here in red that is in the Beltline Road corridor. and talk about each of these drills in more specifics. So some of the other presentations, why did we consider HDD? A lot of it had to do with where we were. So in this Beltline corridor, this is one of the busiest roads in the city of Coppell. It's 4-lane divided and 6-lane divided, depending on where you are. So lots of traffic, lots of development as well. So pretty much all around us, it was the areas were already developed, and we had commercial, retail, we had multifamily and single-family residential all around us. So pretty developed area. There are also some schools nearby and a golf course in close proximity. So lots of activity there. There was a railroad as well that paralleled Beltline Road on the north side. So we really were restricted to the north of where we could go. And then just lots of existing utilities existed in this corridor, really on both sides of the street. And so we were really left with either the median or the pavement itself as far as where we could do the installation. And then at the end of the day, you know, this was in the city of Coppell, and it was a city of Dallas Force Main. So Coppell wasn't really getting any direct benefit from this utility. And so we were sensitive to that. And, you know, obviously they were gracious enough to allow us to install this force main here in Coppell. And so we wanted to be mindful of that and limit our visibility in the area as much as we could, and our footprint and the amount of disturbance that we would have in this corridor. We also wanted to get in and out as quickly as possible. So all of these things really pushed us to horizontal directional drilling. We looked at open cut scenarios, we looked at traditional auger boring scenarios, and really the horizontal directional drilling was just the best method that ticked all the boxes for us in this particular case. And as far as traffic control, just to touch on this really quickly, you know, it is a busy road, like I mentioned, and so we wanted to at least maintain 2 lanes in each direction. And so that really lended itself to having rolling lane closures versus closing down the whole thing. And we had phased traffic control plans that we used. And we also, you know, we had to look at where would the pipe be strung out and how would we do it? Do we have to do it in sections to keep medians open, or were there median openings that we could keep open during construction? So all of that went into the design process, and even talking about or looking at what are the different types of traffic control we need to use. Is it cones? Is it concrete traffic barriers? So we ended up using a combination of those things, and I'll show you some pictures here in a minute to illustrate that a little bit more. And just given the limited working space we had, we wanted to make sure we really defined the footprint for the contractors as they were bidding this project. And so we included details like this in the plans that showed, you know, these are the limits you have for working space and for the drill pit, the entry pit, and all the different equipment and things that you were going to have as part of the process. And so for those of you who have done HDDs before, you know that it's not just the drill rig that goes into it. It's a lot of these other things like I've got listed here on the screen. And so in our case, since we were limited to the median and we were pretty narrow, we really had to linearize a lot of this stuff. And I'll show you some pictures that show you how this was achieved during construction. So just to zoom in even further here now and just look at this specific section of drills in Beltline Road. So you can see here we've got 4 drills all back to back along this corridor, and you can see a little bit better here just what's around us. So we had a major intersection with MacArthur Boulevard. This first drill was probably the most critical of all of them, just because of that intersection. It's just a major intersection in the city of Coppell. We had a middle school down to the south, a golf course to the north. Here's the railroad running along the north side of Beltline, and then just all of these apartments and neighborhoods and this commercial retail district that was fairly busy. So we had to balance all of these things and keep as much of the roadway open as we could. So going further in, just looking at each drill individually. So the first drill here was 1,140 feet. This is the one that crossed MacArthur. And we tried to optimize the design as much as we can. For instance, here we had an entry pit on the right and an exit on the left, with the purpose of then basically turning around and shooting horizontal drill number 2, going to the right or to the east. And so we tried to limit the installations or the setups or mobilizations that they would have where we could. And in this particular case, we were able to do that. And the second drill was a little bit shorter, and this one is actually the one that they started with, and mostly because it was the shortest drill on the project, had less complications than crossing MacArthur, and it gave them a chance to kind of fill things out and make sure they got the right equipment on site and the right methods and procedures, and kind of nail the process down with this first drill before they attempted the one under MacArthur. So they did this one first and then turned around and shot the one back to the left across the intersection. And then the third drill was, again, a little bit longer now, 1,150 feet. And this one had an entry pit on the left side of the screen, and we went to the right. And so we strung out the pipe to the right side of here. And so you can see there's several median openings along this stretch. And so we had to balance keeping these open versus ones we could close if there was an alternate route, or maybe there wasn't much traffic going through those median openings. We really had to look in detail at how we would sequence this and phase this, and in particular with the pipe string that we had to string out for these. And last but not least, number 4, this one was a little over 1,000 feet. And here we really wanted to have the entry pit on the left side of the screen versus the right, but what you can't see is off the screen to the right is a bridge. And so Beltline Road goes elevated just east of here. And so that really didn't give us any room to string the pipe out on that side. And so we ended up having to put the entry pit on the right side and then drill back towards the west side there. But you know, otherwise just pretty typical to the other drills that we had before us. This one did cross Fairway Drive, which was another intersection we had to contend with, but certainly not on the scale that MacArthur Boulevard was. So those are the 4 drills that we had. And then this plan view just shows you an example of the connection between all of the drills. And so we had a little bit of overlap with each one, with the intent that we would come excavate down after the drills were done and connect them together. And so these were all fused together after the drills were done. And you notice the overlap here. And so we had to think about how we would do 2 drills that overlapped with each other. And so we had to design them so that they would veer away from one another as they got towards these exit pits. And then the contractor would come back down and excavate. This was the GC at this point doing the excavations. They had a drilling subcontractor that did the main drills. Then the GC would come back and excavate down and then have to do a fusing of the 2 sections down in the trench. So that did present some additional challenges with this project of having to do a fusion down in the trench, but they were able to make that work. So a few pictures now just showing you what this actually looked like in construction. So again, you can see here how they had to linearize this whole operation. So you have the rig, and then you've got the watering truck and the mud and recycle unit, the job trailer, additional work trucks, and an excavator too, which you can't see right now behind the rig. But all of this was kind of linearized as much as possible because we really only had 40 feet between the 2 innermost lanes and the median to work with. So that's not a ton of working space or width that they had to use. And so they had to get creative with how they would strung that out. And you can also see how we use a combination of these concrete traffic barriers and then cones to protect the work zone itself and the equipment. The biggest concern was just leaving it overnight. And so wanting to have those concrete traffic barriers up and in place to protect the equipment overnight. And then we went to cones once we were outside of the work zone so that we could have, the work vehicles and things coming in and out and give them a way to ingress and egress out of the working zone. It's another picture here just a little further up, just so you can see again how limited the space really was. You've just got those 2 innermost lanes and then the median to work with. And so not a ton of space here. And this is just looking back the other way at the rig itself. And I think this was that first drill that they did, the HDD number 2 is what we're looking at here. And just fun fact here, this is a mini rig. and the project really probably required a maxi rig in terms of the pulling forces, but because of the limited working space that they had, the contractor elected to bring a mini rig out there and start with that. And then they had to bring a wrecker tow truck in to basically brace that mini rig and support it as it was doing the drills. And so they felt comfortable doing that because they had a maxi rig available that they could bring in, you know, at the drop of a hat if for some reason this wasn't working for them. But it ended up working pretty well, and having that mini rig on site gave them that much more space than having to deal with a maxi rig for this particular project. Here's just a close-up of some of the other, you know, vehicles that you have in a typical horizontal directional drill setup. This is the water truck, and again, these are not small things, so you have to think about where all this is going to go. And luckily, we had those two innermost lanes that we could use for ingress and egress, and just stage all of this in a linear way. Same thing here with this flatbed trailer and truck, which they use to bring in supplies. And so just a lot of other vehicles involved besides just the drill rig itself. And so here's a shot of some of the pipe strings and how they did that. So in this particular case, you can see this median here was one that we were able to close. And so they were able to string out more of the pipe. I have some other pictures. This is just looking back the other direction there, back towards the drill rig, which you saw in a previous photo. Here's another example. This is horizontal directional drill number 1. Again, we were able to string out quite a bit in this particular drill because this median here was not really used. There was nothing that it really went to at this point in time when we did construction. So we took advantage of that to close it. But here's an example. I think this is either drill number 3 or 4 where we didn't have as much space. And so we had the pipe in sections and staged right there, and then they would fuse it as they went along. And so this gives you a good picture of that operation and also what the fusing machine looked like. So that I'm gonna hand it over to Marty to talk about the Woodson Village project.
Great, thanks, James. All right, let me get my screen pulled up here. Okay, great. All right, so you've seen 4 case studies, all of which were wastewater force mains, fairly large diameter, medium to large diameter, long pools. This last case study is a project using smaller water main for using HDD for water main replacements in a neighborhood. So this is the Woodson Village Water and Wastewater Rehabilitation Project is just a neighborhood replacement water mains and wastewater mains that were constructed in the 1950s, and it's time for replacement. And so you can see the aerial image of the neighborhood outlined there in red. This is in College Station, Texas, home of Texas A&M University. And it involved about 17,000 linear feet of 6 to 12-inch water main replacement. And we're going to really focus on the portion that was installed by horizontal directional drilling. You can see about 2,300 feet was installed by HDD, but these were in much shorter segments. And so the reason that we were using horizontal directional drilling in this neighborhood was to avoid large trees, other landscaping, driveways, intersections, things just to minimize disruption to this very, well-established neighborhood. We also utilize pipe bursting on the water side as well in areas where we could do that. And then on the wastewater side, majority of the wastewater mains were also installed by pipe bursting in order to minimize disruption to the neighborhood. So we got to use quite a bit of trenchless technology on this project. So as I mentioned, the majority of the areas where we utilized it was to kind of in short segments, typically probably from 50 to 100 feet HDD drills to minimize disruption to trees like are shown here on this exhibit. And so in this area, we were installing the water line just a couple of feet behind the back of curb. majority of this is being installed by open cut through here. And I think this particular existing water line was only a 2-inch water line. And so where we had 6-inch water lines in the neighborhood, we were utilizing pipe bursting as much as possible, but you really can't pipe burst a 2-inch up to an 8-inch. And so where we needed to replace it with new water mains, a larger size, then we were utilizing open cut and directional drilling. So again, this is kind of the typical example of areas where we would use directional drilling on this project. This is the plan view of that same area. And so you can see the two trees with their canopies kind of shown there, and the 48 linear feet that we called out to be done. We didn't actually specify that horizontal directional drilling was the only trenchless option available. We called it out as by other than open cut, BOTOC. And in the bid form, we gave them 3 options. We gave them the option to do horizontal directional drilling, traditional auger boring, or impact molding. So those were 3 options that we had detailed specifications for each of those options. And we left that up to the contractor to basically be able to get the best bids that we could for whatever equipment that they had, or that they could bring in, the right sub to be able to do these short, trenchless segments. So this is the rig that they brought in for the horizontal directional drilling for those short segments. This is, one of those mini rigs. This is smaller than the one that James was just talking about, the mini rig that they used on the Cypress Waters project. This one can easily do 8-inch, probably 8 to 10, maybe even up to 12-inch diameter HDD drills. They do make rigs that are smaller than this. You'll see the telecommunications companies use, smaller rigs for, 4-inch lines, or, smaller cables that they're conduits that they're putting in the ground. But this is what they utilize for these 8-inch waterline drills. Like I said, the longest one was probably about 120 feet on this project, until we got to this next example that I'll show you. But I'll show you that after I talk a little bit about another piece of equipment that is actually available on the market. They do make some pit launched HDD rigs. So these are smaller rigs for smaller installations. This is equipment that can be acquired through TT Technologies, but I'm sure there are other manufacturers who have similar type of equipment to be able to do a small directional drill from a pit. And this allows you to keep it shallower, so it doesn't have to go as deep when you're doing the surface launched drilling, because of the angles that you have to come in, entry angles and exit angles and so forth. So the next one, I wanted to talk a little bit about, so as I mentioned, most of the 8-inch water lines that we were replacing in the neighborhood, we had proposed pipe bursting. And so this 8-inch line along Holloman Drive was one of the ones that we initially proposed pipe bursting. And this was about 900 feet. So it was one of the longer segments that we were replacing, and we had specified it as pipe bursting. But when the contractor got out there and started doing some of his investigations, he discovered that there was an existing 4-inch gas line that was a little too close for comfort. So we did identify this in our design, and based upon the record information that we had, we thought that we had 3 to 4 feet of clearance from the water line, and for the majority of the way. But when they started doing some investigation, they discovered that in some areas that gas line kind of swerved around, and they had less than 2 feet of clearance from the water line. And so with that little amount of clearance, they were uncomfortable with proceeding with pipe bursting. But then the contractor proposed, he said, hey, why don't we utilize horizontal directional drilling to install a new parallel water line for this segment as well. And so that's what we ended up doing. We made a change in the field. And once we made that change, it actually ended up in a cost savings to the owner, because the unit cost for pipe bursting for the 8-inch water line was about $126 a linear foot for this project. And the HDD installation cost was about $80 per linear foot. So you can see there was pretty good cost savings or cost difference between the HDD and the pipe bursting. And part of that had to do with, you know, the pipe bursting equipment as well as the pre-chlorination and some of those things. And so, you know, the owner did end up with a credit, but there were still some other things that had to be, you know, included in the HDD cost that brought it up a little closer to the pipe bursting cost. But as we, I'm going to show you some photos of that particular drill. So this is on Holloman Drive. This is the entry pit where they would excavate in order to have the drill rod go in and the drill bit started there. Holloman Drive is actually a 3-lane roadway, and it's fairly busy. It's got 1 lane in each direction, and then it's got a 3rd turn lane in the middle that you can see here. And so we were able to, you know, do that installation of that parallel line kind of in the outside part of one of the lanes, and then they were able to keep two-way traffic going utilizing that middle turn lane. So this photo here, you can see the traffic control up here on the right part of this photo, where they've got 2-way traffic utilizing that turn lane and the other lane, and then they close down, you know, the 1 lane for the HDD drill rig there. The next photo will show that, and there are some areas as we went further down, like I said, this is about 900 feet. As we went further down, they were able to, in some areas, install the water line behind the back of curb, which saved a little more space as well. So that's the photo there on the left with the drill rig and the drill rod you can see going into the entry pit. And then the photo on the right is a photograph of the reamer, you know, where they back reamed for that 8-inch water line. And so you can see what that looks like as it spins and makes the hole bigger. And then there's the hook on the end of it, or the opening notch where they can connect the pipe that they're pulling into place. And so those are the projects that we wanted to share with you today. I think we've got plenty of time to entertain some questions. And so I'll go ahead and have my co-presenters come off of or get back on screen, and then we can start looking at some of the questions that you've posted, and or if you want to ask as we've got some time here. If we go back, I'm trying to pull up the questions here. Looks like the first one that I saw had to do with how do you decide between microtunneling and horizontal directional drilling? So that's a good question. You know, one of the major differences between horizontal directional drilling and microtunneling. Horizontal directional drilling is typically, you know, the equipment is on the surface and, you know, it launches down into the ground, and typically, you know, it's steerable, but it's, you know, you're not going to be able to put it on a really flat grade. You know, if you wanted to install something like a gravity line, typically, if you're wanting to put something on a really flat grade, and it's also got to be the right size, because microtunneling, you know, will typically be in that mid-range size, and then going up to as large diameter as you want to. Even though it's called micro, it can actually be, you know, very large diameter. But micro has to do with the fact that it's controlled. You know, the controls and everything are on the surface, and you have to install an access shaft, and then it can be drilled on a flat grade and steered very accurately. So that's one of the differences between the two. Cost is probably another big difference. The cost for the directional drilling equipment is much less than the microtunneling equipment and the expertise for that. So microtunneling is typically going to be a lot more expensive.
Yeah, Marty, I'd just add on to that as well. Just one of the projects I'm working on in Oklahoma City right now is a microtunnel project, and we're using it because of the soil conditions. So we have very sandy, non-cohesive soils, and we also have groundwater in the mix. And so you're really talking about the difference between open face methods versus closed faced methods. And so things like HDD and traditional auger boring, those work great if you don't have the kind of conditions we have now where you can't really rely on the surrounding soil and you've got groundwater. And so that really lends itself to a closed face method like micro tunneling. And so those are some of the conditions where you might select it, micro tunneling versus horizontal directional drilling or some other open face method.
Mm-hmm.
I would, and then I guess maybe as a transition to the next question, which is asking about methodologies for minimizing depth for directional drills. Sometimes, I mean, the micro tunneling, if the soils are in the right conditions, I mean, geometric constraints are what are driving you into a tunneling method as opposed to directional drilling. So, so depth on directional drill, I mean, I kind of showed it on mine. We had to start coming up sooner, so we didn't end up miles down the road. So sometimes the geometry of the site and the project dictates depth more so than even if you want it to be shallower. So I think Kyle's project, you mentioned, they able to space it back so that they could get shallower to meet the city's ask. So sometimes there's no choice and you got to switch methods.
Yeah, and to add on to that too, Josh, as far as depth concerns with HDD, so in Cypress Water, the project that I talked about, that was one where we designed it based on a certain depth, basically to minimize the depth as much as we could, but also avoid all the existing utilities and things like that. That was a project where the contractor elected to go deeper as a way to mitigate or prevent the risk of having inadvertent returns pop up, because we were in such a congested, busy corridor there along Beltline. We really didn't want to have any inadvertent returns come to the surface. And what those are is that's just the drilling fluid finding a channel to go through the existing soil and then pop up on the surface. Josh showed some examples of some of that drilling fluid coming down the storm pipe. So depth can sometimes be your friend in that it mitigates some of those potentials for things like that to happen. We also had one spot where we had to extend the drill by about 75 feet because our original design had us going over the top of, Marty, you may remember the size, but basically two very large raw water pipelines for the city of Irving. And the contractor didn't feel good about the additional weight of the HDD above those pipes. And so he elected to just mitigate that risk by going underneath them instead, which then extended our drill out. We reviewed that and at the end of the day agreed that it was best just to go ahead and extend it. But there's things like that that do come up in construction. And so as much as you can work with the drillers and the contractors during design to vet some of this stuff out, that's another good best practice for trying to minimize these changes in construction.
I think too, as you kind of lay out the vertical geometry, don't specify the absolute minimum that can be accomplished. You're going to end up with everyone's going to be disappointed, and you're going to have grumpy contractors and stop RFI, all kinds of stuff going on. So you need to provide some flexibility for the equipment as well as the product pipe.
I think that answered at least partially the second question. The third question that I'm seeing is talking about noise. So for any of these projects, how was noise handled created by the drills? Do any of you guys remember any issues with noise? I don't recall any on the projects that I've been a part of.
I could point out one. I mean, so one of our setups was next to an existing kind of an event venue. And certainly, I mean, they had ample warning. We negotiated easements. We worked through the impacts, but the machines are loud. You have lots of power generation equipment as well as the drill rigs and the mud separation plants, everything. And there's a lot going on. So it sounds like a construction site. And I mean, aside from setting up screening walls like they do around well pads, it's going to be loud. So provide ample warning to folks because it can be disturbing for larger rigs. And like Marty said, I mean, so if you're using smaller rigs in neighborhoods, obviously that dives down a little bit. Or if you have less equipment, and
yeah. I mean, one of the benefits too is that the installation is much quicker than a lot of other methods that especially open cut and or even traditional tunneling methods. It's construction can typically go a lot faster, so the duration of that noise is shorter. The next question I'm seeing here is HDD a viable alternative to auger boring for installing gravity sewer at low slopes less than 0.4%? Are there any cases you're aware of where it's been used to install a casing for a gravity sewer? I would say no. I haven't seen HDD used for a very, especially less than 0.4% gravity sewer. I think that would be very challenging for HDD. Although my understanding is the equipment is getting better and the tracking and steering capabilities of HDD is getting much better, but I don't know that it has that type of capability to get that flat and that accurate.
Yeah, where I've seen it used for gravity, it's like 3% kinds of slopes. It's very steep coming off a mountainside or something like that. That's where I've typically seen it used.
I think pilot tube method would probably be a better option if you're kind of going for that.
Right. Okay, I'm trying to scroll through these. This is not the easiest thing to navigate through here. Okay, any settlement instrumentation or data beneath roadways? Okay, yeah, so that's a good question. Did we have any of our projects where we were required to do any settlement monitoring on any of those roadways, or did we have any issues we're aware of?
So we were for the UPR crossing, we were required to do, and our crossing actually, I think it was 5 different tracks. So three settlement monitoring points on each track. It was no, I mean, when we crossed the tracks, we were 70 feet below grade. So, I mean, minimal issue or, no issues. Now I will point out, I mean, sometimes the railroad had, I think it was a 1/4 inch max deflection or requirement, but the rails deflect more than that when the train goes over them. So it's kind of not a helpful thing, but I mean, it's definitely easy to do. It's a cheap way to monitor that stuff's happening. But I mean, if we're having settlement, there's other issues occurring too. And so I think, kind of like all this stuff is better to get good soils data early. And I would say, I mean, a lesson learned on mine is I wish I had held back a few of our soil borings for once we had completed our design, and then gone out and gotten a few more just to really shore up that data to provide helpful information for construction. So maybe it's budget for more soils data to mitigate some of those things.
Okay, I'm seeing a question about the last project, the Woodson Village one that I talked about. It says, if 2 feet was too close for comfort for pipe bursting, how far did you move the alignment to accommodate HDD? So I believe they ended up just moving to about 3 feet off of the clearance, minimum clearance from the gas line. They were a lot more comfortable with the HDD versus the pipe bursting because of the vibrations that are caused by the pipe bursting, and so they were concerned about that. But we did try to maintain about 3 feet of clearance for the HDD.
Yeah, and I think this probably speaks to the next question too. So for at least with Cypress Waters, one of the things we learned on that one is vertically, at least for the larger stuff, you really want to try to get 5 feet if you can. And that's not just from the pipe, that's from the reamer. So there's a larger hole that is drilled before you pull in the product pipe. And in our case, for a 24-inch HDPE Force Main, that reamer size ended up being like 42 inches. So it can be quite a bit larger than the product pipe that you're designing. And so you do want to take that into consideration. And so 5 feet from utilities plus the size of the reamer, that's pretty quickly 10 plus feet there that you're looking at in terms of separation. So that is definitely a factor to consider.
Yeah, I think on the legacy project that I spoke on in Frisco, we had a horizontal deviation of 4 feet and a vertical deviation of 3 feet was what we required in the spec from the pilot bore. So there's a decent amount of clearance from those utilities.
Now I mean, and what's neat about this technology is there's always a way to get around that if you need to. So on Clear Fork, we required a relief bore basically to be drilled on the exit side with a small rig because we couldn't be, I mean, we were pretty close to a large sanitary sewer interceptor. And so that was a requirement. Now there was some negotiation during construction. The contractor kind of approached it by slowing down, turning off his mud motor. Still worked, but there's ways around that to basically a leaf bore would provide a pathway for that drilling mud to go and not go into the utility or undermine the embedment, things like that.
Mm-hmm. Yeah, and I'm certain that in the best practices course, they would probably have some recommendations on clearances as well. So take a look at that. Let's see. On the big inch HDPE pipe, did you use buoyancy control? The big inch, I like that.
Big inch.
Yeah, I think probably that's on the 42-inch HDPE line. Yeah, we ran the calcs and it did show that we would want the pipes to be pulled, being full of water. So that will be that's part of the requirements of the specification.
Mm-hmm.
I think that's pretty typical. I mean, you have buckling issues if your pipe's not full of water or flotation. I mean, yeah.
Even on the 20-inch, we ended up they got maybe 1,300 feet in the pool, and then they filled it with water to finish out the rest of the pool. So total pool was 1,700 feet.
Mm-hmm. Okay, we've got a question here. It says, was a baseline report prepared for any of these HDD installations? I assume it's talking about the geotechnical baseline report. Not aware that we did a GBR for any of these specifically. We certainly had geotechnical data reports, and we often will also talk to trenchless, specialty sub-consultants and other consultants with the geotech who specialize in these trenchless methods to get their input during the design process, and talking to the contractors during construction as well to make sure everyone's comfortable with that. And then often, if the contractor needs to get additional geotechnical data, prior to construction, then that is certainly encouraged and welcomed. Let's see, next one. Great presentation, thanks. Oh, thank you. I'm curious what sort of location guidance was used. Did Kimley-Horn make any sort of specification about equipment or accuracy requirements?
Yeah, on Cypress Waters, we had a minimum requirement there for a wireline system, which we were fortunate in our case because we had the railroad right of way there to the north. And so they were able to use that as kind of just a wide open area to run that wireline guidance system along the whole length of that corridor. So that really, we took advantage of that available space to use the wireline system. Otherwise, they would have had to have used the gyroscopic system.
It's probably worth pointing out, some folks don't understand what that system is, and someone who's an expert on this call is going to say he did it wrong, but I mean, essentially, like, you have a signal or a current that's being sent out from the bore head or at the face of the bore. You have two wires running down either side. The system can monitor basically distance based on receiving that current or kind of seeing the way it hits this wire versus this wire to understand where it is in 3D space as you're kind of extrapolating that directional data. So it helps to tie in where you are in space. How'd I do, guys? Was that good?
It was understandable, so that's good.
I know Wallen's like cringing. I could feel it.
All right, so next question says, what is the maximum practical elevation differences between the inlet and outlet pits for an HDD installation? And if the project site exceeds these elevation, difference values, are there any measures that can be taken to mitigate the drill fluid runout concerns? Anybody have any question or issues? Or I don't think that any of our projects had any major elevation changes. We're, several of
A
these.
lot of elevation change in Miami, or
Yeah, or in Dallas. Yeah.
haven't run into
But,
that.
not something I think that we've run into on any of these projects, but that is a good consideration to be aware of. All right.
I don't think we can answer the contract labor union costs for workers on projects in Texas question.
Yeah, I'm not sure that we don't have any contractors on our teams or our presenters, but not sure about that one.
I think you missed one question there, Marty. Just largest
Okay, go ahead.
size, the largest diameter pipe installable with HDD.
That's a good question. When you guys in your projects research, what would be the largest you're aware
I
of?
want to say the record was like 52 inches or something. 50, I could be wrong. I'm sure it keeps going up, but it wasn't near as long as any of these drives.
I mean, we looked at it for a 48-inch water line that we did, and it was going to be a steel directional drill, and the size of the steel, the thickness of that steel was going to be prohibitively large, where it didn't make sense from a cost perspective. They had the equipment to do it. It just the cost was not going to work out.
Mm-hmm. Yeah, so we're probably getting limited once you get above, 42, 48, 54. You're probably getting pretty limited in those sizes. Okay, I've got one here. It says, how do you develop bore profiles in the design phase for HDD? And do you work with companies like Underground Solutions to help make sure it's constructible? Kyle, you want to address that one? Because I know you guys work closely with them with the fusible PVC, right?
Yeah, I mean, certainly getting feedback from companies like Underground Solutions is helpful. We've reached out to contractors that we're comfortable with to get feedback on different parameters, entry angles, exit angles. We've pulled actual equipment specifications to understand, hey, what's the maximum bending radius that you can get from the drilling rods. Certainly you've got the pipe, but you also have the drilling rod too. That'll help define what that radius is that you can do. And there's certainly there's design best practices out there that we reference as well, and kind of piece all those together to come up with the design plan and profile that we end up with.
Mm-hmm. Okay. Question I see here says, how do you evacuate mud when you don't have mud recycle? I think I've seen mud recycle on all the projects that I've worked on. Is that something any rest of you guys have seen where they haven't done that?
I think for like neighborhood utility projects, like, you're seeing small gas lines, things like that, I think they don't. And typically it's like in any of these, the mud stays in the hole, right?
Mm-hmm.
And so that's where we want it to stay, because it's denser than water, so it kind of holds that hole open underground. So if you're not recycling, even if you're recycling it, it's still going to a lot of it's staying in the hole.
Mm-hmm.
So.
Yep. How did you deal with the profile of the HDD tying into the open cut portions? And was there any cutbacks to reduce the high, low points in the pipe profile as installed?
Yeah, so specifically on the legacy Force Main project, when I think it was on the exit side, essentially they didn't quite hit the spot they thought they were going to from the design profile, and so they had to make it up. So they went in there and they cut back a little bit, added a fitting and then tied back into the open cut portion to get back to where they needed to be.
Mm-hmm. Yeah, and James, I think you addressed it a little bit with Cypress Waters, where there would be some overlap that they would have to cut off, and then they would lower it into the trench that they would excavate, and then they would fuse it together.
Recycle it, especially if it's fusible pipe.
Yeah. But yeah, most of those force mains, we'd be installing air release valves at those high points generally.
Mm-hmm.
All right, I see Carrie, so that must mean we're getting close on time.
We are. Thank you so much. For everyone that did ask questions, Kimley-Horn's going to have a record of those so they can follow up with y'all to make sure that your questions do get answered. So feel free to keep populating if you do have some remaining stuff, and then we can get that off to them.